Hey everyone, I'm Andrew Mikalsen, and I'll be presenting Coriolis, which is a metagenomic classifier designed for lightweight mobile devices. Our work's motivated by portable DNA sequencers like the ONT Marion to enable real-time and in-the-field DNA sequencing. This has led to applications like rapid medical diagnosis and tracking infectious diseases, as employed in the Zika and Ebola outbreaks, as well as environmental DNA prospecting and many other applications. But to fully realize these applications in the field, we need to perform metagenomic classification alongside portable sequencing. And this requires we deploy metagenomic classifiers on lightweight mobile devices. And this is a pretty challenging task since even though these devices are equipped with powerful CPUs and GPUs, they have several restrictions like their limited main memory, the fact that they need to run IO-intensive software, and that's all happening while they're deployed in environments that have very little or no network connectivity, and they have an additional restriction that they have a limited amount of energy that they need to effectively manage. Unfortunately, even though there are a lot of excellent metagenomic classification tools available, they're not designed for environments that have limited resources like this. They also have monolithic software architectures that make it difficult to decompose and optimize them for these situations. Additionally, they need to use these really large reference databases, which easily exceed the amount of main memory available to the device. With all this said, there have been attempts to deploy these tools in the mobile setting, which usually utilize the memory mapping capabilities that are available by some tools. But even though this may let the classifier run, it comes with some pretty big restrictions. It limits the maximum size of the database index. It uses general purpose techniques to manage the data coming from the operating system that aren't suited for the metagenomic classifier workflow. And even though the classifier may run, it is still designed assuming that all the data fits into memory. And since this is violated in these scenarios and it ends up running out of core via memory mapping, it comes with a pretty big slowdown. To address these issues, we make a few different contributions. The first is SMARTN, which is a programming model for expressing optimized metagenomic classifiers. The second is the compact string B tree, which is a practical data structure designed for performing exact pattern matching out of core. And the last is Coriolis, which is a metagenomic classifier designed for being deployed in these mobile settings. We prototype these contributions as industry-grade software that's freely available and open source from our project webpage. Our first contribution, SMARTN, decomposes the metagenomic workflow using high-level abstractions that are expressive enough to represent virtually any metagenomic classifier. By performing this decomposition, SMARTN separates computation into individual tasks that can be individually managed and optimized, and by doing this, it can automatically parallelize and optimize the execution of the classifier. As a result, the programmer only worries about the high-level classification algorithm, and all the details about how that algorithm maps down to the underlying hardware and how data is managed is done by the SMARTN runtime system and the programmer doesn't need to worry about it. So when writing a SMARTN program, you think of the classification process from the perspective of a single read. So this process is decomposed into 4 stages, and the programmer implements a method for each of the stages that tells the SMARTN runtime how to process data at that stage. So the first stage is read preprocess, which does some initial preprocessing of the read, like filtering reads and identifying segments of interest within the read. And after that is match search, which does some initial searching in the reference database for portions of the read. After match search is an optional match extend stage, which further inspects matches identified in match search, a classic example being extending a match found as far as possible. And finally is label assign, which utilizes all the evidence identified in the previous stages and aggregates it together to determine the final taxonomic assignment for the read. And while this process may seem simple, it's powerful enough to express virtually any metagenomic classifier. And since it decomposes computation into these individual tasks, Smarten is able to automatically parallelize and optimize its execution, and the programmer doesn't need to worry about these underlying details. And additionally, even though the programmer only thinks of classification from the perspective of a single read, in reality, a Smarten program operates on a stream of reads, and this is done transparently and adds another dimension of parallelism that Smarten exploits. So, to give you an idea of what a Smarten application actually looks like, here's an example of instantiating and running a Smarten application. Smarten abstracts input and output in terms of iterators and provides several different types of iterators, like FASTA, FASTQ, and FAST5 iterators, and even iterators that automatically read input streamed by the base caller or the sequencer, to allow you to easily deal with the input data without having to worry about how it's actually managed. The programmer defines 4 types corresponding to the 4 stages of the workflow, and each of these types has a static run method that tells the Smarten runtime how to process data for the corresponding stage. These types are combined into a Smarten app object, which is used to actually launch the application. And after the execute method is called on the Smarten application object, the entire execution of the classifier is afterwards handled by the Smarten runtime. This is what a Smarten stage implementation looks like. In this case, it's the read preprocess stage that we use for our Coriolis classifier. And you can see that this run method takes a read ID and a read of types defined by the programmer, and a Smarten runtime object, which is used to interact with the Smarten runtime system. This implementation filters out short reads and then creates a match search task for the read and its reverse complement by using the Smarten runtime object. The Smarten runtime object can be used to create tasks for any stage of the workflow, including outputting taxonomic assignments. So, while Smarten allows us to implement optimized metagenomic classifiers rapidly, there's still the major algorithmic challenge of how we manage the reference database in mobile setups. As I'm sure you're all aware, these reference databases can be massive and they're rapidly growing. Yet, the amount of memory available to mobile devices is extremely small, and it grows much slower than the rate at which these reference databases grow. Even for the high-end mobile devices, it's easy for the reference database to exceed 16 times the amount of available memory, and this isn't even considering how in real deployments, the metagenomic classification algorithm doesn't have exclusive access to the memory, but the memory also needs to be shared between the system itself and other software like the base caller. So we can't expect to fit the entire database into main memory, and so we need to have some solutions to deal with these restricted memories. The solution we propose is to use external memory, like SSDs and NVRAM. These come at large capacities for relatively low costs, and they're relatively energy efficient, since unlike RAM, which consumes flat energy, these devices only consume energy when reading or writing. So we're able to scale up the storage capacity at these low costs and without much energy overhead, which allows us to store the database on the device. But the issue becomes that reading from storage is much slower than reading from RAM, so we need to use algorithms that are able to efficiently search the database when it's stored on disk. We do this with the compact string B tree, which is a practical data structure for performing exact pattern matching out of core. The compact string B tree can be seen as a B plus tree over the values of the suffix array, where these values are stored in the leaves and then replicated at higher levels of the tree. So to reduce the size of this tree, when we have duplicate suffixes, like for example A, we have 11, 3, and 18 that all correspond to the suffix A. We only store one of the representative suffixes in the tree, and then all duplicates are stored in an external array, and we have a pointer from the representative suffix to the list of all its corresponding duplicates. The internal nodes store for each child the rightmost suffix associated with that child, and then to search the compact string B tree, we follow an algorithm very similar to searching a B plus tree, where starting from the root, we identify the successor of the query pattern, and then we descend to the corresponding leaf node, or the corresponding child node, until we reach a leaf node. Afterwards, we scan the leaves until we identify all occurrences of the query pattern. Now, identifying the successor within a node may require many I/O operations, since every string comparison requires an access to the text, which is also stored on disk. So to remove these excess IOs, every node's embedded with some auxiliary data, such as the LCP information and the character mismatch information. And as we've proven in the paper, this information is sufficient to identify the successor of a pattern within a current node with only a single access to the text. And as a result, we achieve the provably optimal number of IOs under the external memory model. And the consequence of that is not only that searching this data structure is fast, but it's also energy efficient, since every IO operation corresponds to some amount of energy usage. To give you an idea of what the performance of the CSBT looks like, here's a comparison between the SBT, the suffix array, and FM index, where we vary the DMR, which tells you how many times larger the input text is than the amount of available memory. And we see that the compact string B tree performs less IO operations than the other data structures and is faster. And as a result of performing less IOs, it's also more energy efficient. We combine Smarten with CSBTs to design and implement Coriolis, which is a metagenomic classifier for mobile devices based on exact pattern matching. Coriolis can run even when memory is extremely limited, including less than a single gigabyte. It's able to perform effectively using noisy min-ion reads, and it's even capable of running in real time alongside the base caller while using massive reference databases. To evaluate the performance of Coriolis, we set up an experiment where we simulate monitoring algae pollution using a reference database of the relevant algae and bacteria genomes. For input reads, we have 3 mock communities of various densities of algae versus bacteria, and we sequence these mock communities using min-ion to obtain real min-ion reads. This data is available from our project webpage for anyone who wants to use it. We run our experiments on an NVIDIA Jetson TX1, which has 4 GB of RAM, a 4-core ARM processor, and we equipped it with 4 terabytes of SSD that were attached over SATA 2. And this gave us, when benchmarking, approximately 250 megabytes per second. And since the peak theoretical throughput of SATA 2 is about 300 megabytes per second, this is about what we would expect in practice. To evaluate the speed of classification, we use the real min-ion reads we obtained by sequencing our mock communities, and to determine what the effect of the database size is on the speed of classification, we varied the DMR throughout our experiments. When evaluating the effectiveness of the classification, we use NanoSim to simulate reads from our real min-ion reads. We compared Coriolis to Kraken Unique, Kraken 2, and Centrifuge. The top table shows the throughput of each classifier for different DMR values, and the bottom table shows you the effectiveness of classification. We see in the top table that Kraken Unique runs pretty well for low DMR values, but as we increase the DMR, its performance quickly goes down and it's eventually not able to run. Kraken 2 runs for all DMR values, but its performance still decreases as we increase the DMR, and it's noticeably slower than Kraken Unique. Centrifuge, even though it uses compressed data structures to try to fit the entire index into main memory, it's slower than all the other tools, even for low DMR values, and it doesn't run at all for higher DMR values. Coriolis is faster than all the other tools across each dataset, and its performance doesn't decrease as we increase the DMR. In fact, if we look at 52 DMR, which corresponds to the scenario where for every gigabyte of main memory, we have 52 gigabytes of reference data, Coriolis runs at nearly the same speed as when we run with a DMR of 3.25. In the bottom, we see that Kraken Unique and Kraken 2 are noticeably worse than Coriolis and Centrifuge, and we suspect this is because the Kraken-based classifiers use matching of k-mers of a fixed length, while Centrifuge and Coriolis match sequences of an arbitrary length, and as a result, they're more resilient to errors that occur during sequencing. Also, in the most recent version of Coriolis, we're able to run it in real time alongside the base caller while using the entire ABV database. In this video, we have Coriolis running in the bottom left, we have Dorado, our base caller, running in the top right, and we have the output of Coriolis in the bottom right. And as you can see, Coriolis is able to classify the reads in real time as they're produced by Dorado, even though it's using the massive ABV database. So to wrap things up, if we want to employ the applications of portable DNA sequencers truly in the field, we need to couple it with in-the-field DNA classification. And this introduces many challenges due to the limitations of mobile devices. To deal with these limitations, we propose Smarten, which lets you rapidly implement optimized metagenomic classifiers, the compact string B tree, which can be used for deploying massive databases on mobile devices, and Coriolis, which is a classifier for real-time analysis of DNA in these mobile settings. All of our tools are open source and freely available from these web pages, and so if you're interested, feel free to access them. Thank you.